Hello everyone. So in this video we'll discuss about the instrumentation amplifier. So before proceeding to the instrumentation amplifier, so first we'll see what is transducer. A transducer is a device which converts one form of energy into another form of energy. So for example, a microphone. A microphone converts a sound energy into an electrical energy, and then thermocoupler which converts an heat energy into an electrical energy. So this electrical energy which has been transformed by transducer are used to control and operate the other parts of the system, or it can be used to get display or recording of some measured physical quantity. So the output of the transducer, that is electrical signal. So these electrical signals are used to control some next stage, other parts of the system, or can be used to get displayed or for recording of some physical quantity. Okay, but the output of the transducer are very low level signals, that is the electrical signal from the transducer are very low level signal, such that these low level signal cannot be drive sufficiently cannot be drive by the next stage. So hence such electrical signal from the transducer need to be amplified, so rejecting the noise and interferences before proceeding to the next stage. So the special amplifier used for such low level amplification, we call it as instrumentation amplifier. Okay, it's a kind of differential amplifier. So in brief, instrumentation amplifier is a special amplifier used for low level amplification of an electrical signal which is the output from the transducer. Okay, output of the transducer is an electrical signal. So these electrical signals are like very low level signal. So to amplify such low level signal, we use a special type of amplifier called instrumentation amplifier. Okay, so it is a kind of differential amplifier. So differential amplifier is, it find the difference between the two inputs of the two terminals input. So and it amplifies the difference between the input voltage of the op-amp. Okay, so that is operational amplifier. So low power consumption, high CMRR and high slew rate are the desirable for superior performance of an instrumentation amplifier. So for we'll discuss an example of an instrumentation amplifier using transducer bridge. Okay, so this is an differential instrumentation amplifier using a transducer bridge. Here we have a bridge, transducer bridge, and this is the op-amp part, that is amplification part, and this output is used to indicate some meters. Okay, some display has to be happen, or it need to show some readings or something like that. Okay, so output of a transducer is amplified in this part, and this amplified signal is used to indicate or display something. Okay, now so a resistive transducer, resistive transducer where resistance changes as a function of some physical energy is connected to one arm of the transducer bridge. Okay, so this is a transducer bridge. Okay, it consists of 4 arms, RA, RB, RC and RT. So this is a resistive transducer where the resistance varies as a function of some physical energy is connected to one arm, so which we represented by RT plus delta R. Okay, where RT is the resistance of the transducer and delta R is the change in the resistance. So that is due to some physical quantity. If some physical energy changes, so this resistance will also get changed. Okay, so now the bridge in the circuit of the figure is said to be excited by the DC power supply, or could be AC excited as well. So for the balanced bridge, for some condition, for balanced it's for some reference condition, VB is equal to VA, that is VB. So this is the output from the bridge is given to the two amplifiers, two op amps. Okay, so this is VA and this is VB. Okay, so for under balanced condition, VB is equal to VA. So where VB is given by, so the voltage at this is given by, so VDC we have connected here, so RB divided by RB plus RC, since it is connected over here, this terminal, that is potential at this terminal is determined by these two resistance along with the DC voltage VDC. So VB is equal to RB into VDC divided by RB plus RE, whereas the potential at this terminal, that is VA, is determined by these two resistance. VA is equal to RA into VDC divided by RA plus RT. So delta R, this is not, since we are referring to the balanced condition, we have not given delta R. Okay, so by the Wien bridge we have solved. So if you solve this equation, you will get it as RC divided by RB is equal to RT divided by RA. So this we have solved it in the Wien bridge. Okay, so next, okay, so generally the resistance RA, RB, the RA, RB, RC are selected such that they are equal to the transducer resistance RT. Okay, so I said the reference condition. So reference condition is something, it is a physical quantity under measure at which the bridge is balanced. So reference condition is a specific value of a physical quantity under measurement, so at which bridge is balanced. Okay, so that is some input physical quantity that should be measured. So under that condition, under that specific value, so the bridge is balanced. Suppose the bridge is balanced initially at some reference condition, okay, at some physical value, so the bridge is balanced. But as the physical quantity to be measured changes, okay, so whatever the things we need to measure changes, the resistance of the transducer also changes, that is RT will change, so which causes the bridge to be unbalanced. So when the value of RT changes, the bridge will not be balanced. So under that condition, the change of the resistance of the transducer be delta R. Okay, from RT it changes to RT plus delta R. Since RB and RC are fixed resistance, the voltage VB is constant. Here, so only these are all the fixed values. RA, RB and RC are the fixed values. This only the RT is a variable resistance. So since VB depends on RB and RC, so the voltage VB will not change. Only the voltage VA will get changed due to change in the transducer resistance. Okay, so that change in the transducer resistance is given by VA is equal to RA into VDC divided by RA plus RT plus delta R, and VB is equal to RB into VDC divided, this remains the same as previous. So now the voltage VAB across the output terminals, that at the output terminals of the bridge is VAB, VA minus VB. Okay, so under balanced condition VA is equal to VB. So under unbalanced condition VAB, there, that is the difference in the, there will be a difference in VA and VB. So that what is the difference we'll see now. RA into VDC divided by RA plus RT plus delta R minus RB into VDC divided by RB plus RC. So if we take RA, RB, RC, RT is equal to R. So that is all the resistance are same. So then upon solving this we get VAB, the difference between the voltage VA and VB, we get it as delta R into VDC divided by 2 into 2R plus delta R. Now, so this is the output voltage of the bridge. This is the output voltage of the bridge. Okay, so this output voltage we are applying it to the op amp. So that is amplifier which consists of 3 op amps. See, that is the output voltage VAB of the bridge is then applied to the differential instrumentation amplifier composed of 3 op amps. Why it is called differential instrumentation amplifier is, so we are applying the difference input to the 2 op amps. So that's why it is called differential input amplifier which consists of 3 op amps. Now we have already derived the gain of the basic differential amplifier is minus RF divided by R1. That is the output of the circuit, that is output of the op amp is given by VAB input minus RF divided by R1. Okay. So that is delta R into what is VAB, what is a delta R VDC into 2 times of 2R plus delta R RF divided by R1. So that is V0 is equal to A into V in. So V in is VAB. Okay. So since 2R plus delta R, the change in resistance of the transducer is very small. So 2R plus delta R, we can write it as 2R. So that will become 4R. So this equation indicates that the change in VDC, that is the change indicates that V0 is directly proportional to the change in resistance of the delta R of the transducer. So if delta R changes, V0 will also changes. Okay, so that is if delta R, so the signal, if the signal gets, that is the V0 will get amplified. This is the gain of the amplifier. RF divided by R1 is the gain of the amplifier. So the output, so the change in delta R will also change in V0. How much times? The gain of the amplifier times the V0 will change. So if delta R is, there is a small difference in delta R, there is small change in RT, that is R. So V0 will also change this many times. If delta R has largely changed, that time also it will change RF divided by R1, that is gain times. That is, we are saying that, so this change in resistance is amplified by RF divided by R1 times, that is gain of the amplifier. Okay, and the application of instrumentation amplifier, it is used as a temperature controller, temperature indicator, light intensity meter, analog, weight scale. Thank you.